we're going to look at another example of how to calculate potential. And I just want to be really clear about what we did at the very end of the last one. At the very end of the last one, what we said was the potential due to a point charge is Q over 4 pi epsilon 0 r. So this equals V of r for some charge at when you're some distance r from a point charge. Remember, this is assuming that the potential at infinity is set to be equal to 0, but that's our normal assumption. So we probably won't even really need to worry about that in this class. There are times when, for our problems, when that becomes important, what your assumption is there. For this class, we probably won't get to any problems where there's really an issue. But in any case, so basically what I'm saying is we're just going to say this is the potential of a point charge. Just bear in mind that it could be this plus or minus any constant value, right? We could set 0 to be anything we wanted it to be. So I've beat that into the ground enough, I believe. Okay, so why is this important? Well, this is important because now that we know what a point charge potential is, we can now calculate the potential of anything. Same way we could do with the electric field. We could calculate the electric field of anything once we knew the electric field of a point charge. All we need to do is add the individual things together. Superposition, which we looked at in a few videos ago. Okay, so what if I have a charged ring? I believe in your book this is example 23-8. I am going to do it a different way than your book does, just so you see there's a different way to do it, so you can look at that as well. So I'm going to go ahead, we'll go ahead and use the same coordinate system that your book uses, but I am going to do something a little bit different. Because what I'm going to do, what we are told is we have a uniformly charged conductive ring. It has some diameter, I'm going to call it R0 again, excuse me, some radius. It has a radius R0. It however has no, it's just a line. So there is no dimension, there's no like delta Z here for thickness. There's no thickness of this, it's just a line that's uniformly charged. It has a total charge of Q. So the question is, what is the charge density on this? Well, if it's a uniformly charged conductive ring, has a total charge of Q, its total length is 2 pi r0, so its charge density is Q over 2 pi r0, and this equals, let's see, what do we call that? Lambda. Okay, so now we know that, and now the question is, what is the potential at some point along the axis here? Well, here's the potential from one charge is this. What we're going to do is we're going to take charge here, we're going to add it to the charge here, here, all the way across. And of course, you know that the way that we do this easily is by using the tools of calculus. So instead of looking at finite bits of charge and trying to add them up, we take an infinitesimally small bit of charge and we add that together. So what we are going to have is we are going to say our total potential at point R is going to equal the integral of yeah, you know what? I'm going to write it like this. I don't think this is a traditional way to write it, but I'm going to write it like this, of dV, but what is a little bit dV? What's the little potential, the little bit of potential that's added by that point right there is just this expression, dQ over 4 pi epsilon 0, and all right, I'm just going to say R for the moment. Okay, and then the question is, well, what's our dq? So let's look over here, and what do we have? We have our dq for, let's look flat on this circle right now. Okay, so there's our circle, there's our y and z, and we've got some density lambda here, and our dq for this little bit right here is just, what do we call this, R0? Yeah, R0 d theta. Okay, so that's it. That's all we have is R0 d theta. All right, so that's dq is going to be lambda r0 d theta. Let me make sure that's in the video. I can't see it as I'm recording it right now. So that's going to be our dq. So now we need to look at, what else do we need to look at? We need to look at our r, because our r might be changing too as we do this. Well, let's look at, let's go ahead and make some space. Let's see. I'm going to go ahead and write this over here too. Lambda equals q over 2 pi r0. All right, so then we can get rid of this stuff here and I can have some room. Okay, so now let's go ahead and look at this integral. This integral is now going to be equal to, let's see, lambda is a constant. R0 is a constant, lambda R0. 4 pi epsilon 0 is a constant, so I can pull all those out. And then the question is, what is the R from here to here? Okay, so I think it's pretty easy to see that no matter what the theta is, this distance here, I mean, if we're going to really do it right, we would say it's x, x doesn't change. We would say that this distance is equal to y squared plus z squared minus, if we were going to do a vector, we'd say minus, but we're just doing the distance, so plus x squared, right? Where we're going from here to here, and the point, I'm playing a little bit fast and loose. The point here is that y and z are equal to 0, and the point here is that x is equal to 0. So when I say x, I actually mean this specific point right here, x. When I say y and z, I mean any point along this where there are different values of y and z. But what is the definition of a circle? Y squared plus z squared equals r squared. So what this really is this, and then the distance, of course, the r would be the square root of that. Okay, so what do I really have here? What I really have is this r here, this r right here is just going to equal the square root of r0 squared plus x squared. Okay, so now I just have this 1 over square root r0 squared plus x squared. And what do I have? Oh, and what's left in my dq? The only thing that's left here is d theta. Where am I going to integrate over? I'm going from 0 to 2 pi. All right, so this is done. All you need to do is do this integral. We look at this. Are any of these functions of theta? No, they are not. So I can pull that right out of the integral. All I get out of this integral is 2 pi. So now let's go ahead and do this. So now we can say that the v of r equals lambda r0 over 4 pi epsilon 0 1 over square root r0 squared plus x squared d, there's no d theta, times 2 pi. Okay, and so what do we end up with? We end up with v of r equals lambda over 2 epsilon 0 r0 over square root r0 squared plus x squared. Okay? No, it's not okay. Oh yeah, no, it's great. It's great. Sorry, because now what is this? we look at this, we look at lambda. All right, I scared myself for a minute there. Now we're going to rewrite this because we know what lambda is. And so things are going to be looking good in just a minute. I'm going to go ahead and get rid of this term here. So we now have V of R, and all I'm going to do is substitute in this expression for lambda. Lambda is Q over 2 pi R0, and I have, so that's, 2 epsilon 0 here. I have an R0 over square root R0 squared plus X squared. There we go. Now we're looking good. Okay, and so what happens here? R0 cancels with R0, and now we get to an expression that we have seen. Well, let's just, I was going to say we've seen it before. We haven't quite seen it before, but let's go ahead and do this. All right, so Q over 4 pi epsilon 0 1 over square root of R0 squared plus X squared. Okay, and this is our V of R. It might be interesting for you to do this, dV dx, and see what expression you come up with. What should you come up with? What should this be? Well, this should be an expression for the electric field, right? The gradient of V is an expression for the electric field. Okay, so I'm going to leave that for you guys to do, but there is one other thing we can do. We can look at this and say, you know, what happens if X is really big compared to R0? So what if when we're looking at this, we are so far away from this little thing here that it looks like just a tiny little circle there, but we're way over here. Yeah, we're way over here. Okay, so what happens, what that means is we can ignore this R0 squared, and we'll square root of 1 over X squared is just 1 over X. So this equals, so our V sub R equals Q over 4 pi epsilon 0 X. But X in this case is really just R, right? It's just the distance we are away from this. And in this particular case, you'll see if we do that, this is exactly what we would expect for a point charge here of magnitude Q. And that's what we would expect to see, because as we get further and further away, that circle looks more and more like a point. Okay, that was 23.8 done a different way than your book does it.